Welcome back to 2D Mat, 2D Materials in Tribology. We're happy to present our first tandem webinar with Professor Dr. Vadim Mochalin, who will speak about mechanical properties, adhesion and superlubricity of MXenes, and with Professor Dr. Ashlie Martini, who will speak about atomistic mechanisms of friction for MoS2 and beyond. Before we start, we want to thank our sponsors for their support. We are sponsored by the two MDPI journals Coatings and Lubricants, as well as Frontiers in Mechanical Engineering and Arctic Instruments.
Ashlie Martini is going to join us in a few minutes because she's still in class. That's why we're going to start with Professor Dr. Vadym Mochalin. I would like to introduce him and say a few words about him. Vadim has received his bachelor and master in biochemistry. Afterwards, he has done a PhD in physical chemistry, both in the Ukraine. Like 15, 16 years ago, he moved to the States, to Philadelphia. His research group is mainly focused on the fundamental physics and chemistry of materials at the nanoscale. He's an expert for nanodiamonds, for MXenes. He has reached more than over 18,000 citations with an H-index of 44, according to Google Scholar. And we are very much looking forward to learn a little bit about superlubricity of MXenes.
Good evening also from my side, and welcome to 2D Mat. Just a friendly reminder before we start, we ask all participants to keep their audio on mute and also the camera off, and apart from the host and the speaker. So yeah, thank you very much, and we're looking very much forward to the talk of Professor Mochalin.
All right, am I good to go?
You are good
yes,
to go.
The stage is yours.
Very good. Thank you. Thank you, Andreas. Thank you, Philip, for organizing this wonderful series of webinars and inviting me to give a talk. Also, very nice introduction, Andreas. Thank you. When I hear it, everything looks good. But when you say 15, 16 years, I'm like, wow, time flies. So yeah, I'm working in Missouri University of Science and Technology right now in chemistry department. And let me start with a brief introduction of my group. So what we are doing here, what we are experts in, and what is my research currently focused on. So we are experts in low dimensional materials, I would say. We work with all kinds of materials from 0-dimensional to 2-dimensional materials. And current research is focused on fundamental understanding of physics and chemistry of these materials, using Raman spectroscopy to, again, understand their properties, computational modeling. And then we use this knowledge about physical and chemical properties to develop applications. And applications vary from extreme environments to energy, catalysis, sensing, optical, biomedical, and more. So these are the journals we published our research in, and currently I also serve as editor of Diamond and Related Materials, published by Elsevier, and Scientific Reports. So as I said, we work with all kinds of low-dimensional materials, and I found it more aesthetically pleasant and shorter, actually, to introduce to you all these kinds of materials just by showing these cover pages from two journals.
Vadim,
and these cover pages summarize.
I'm sorry, because we are not seeing the presentation of you.
Oh.
Yeah, I'm sorry to interrupt you, but...
No. It would be worse if you don't tell me.
I thought in the beginning when you said that you want to give a brief introduction, I thought that you were would be saying some words, but then I realized that we were supposed to see something. So now we are seeing your presentation, yeah.
Good. it's good that you see this slide because the images are really beautiful. So these are different materials we work with. And you can see here, for example, on the left image, a structure of carbide, transition metal carbides, silicon carbides, a structure of amorphous carbon here on the right top, in the right top corner, a structure of carbon onion produced from nanodiamond here, of course, nanotubes and two-dimensional materials, graphene, boron nitride, and on the right image, you see a flake of MXene, multi-layered MXene. SEM image blended with results of computational modeling of lithium intercalation into MXene. So these are materials we work with. And my talk today will be focused on just one part of our work, which is related to MXene. And this slide introduces MXenes to you. I don't need to give a long introduction after Professor Gagotz's talk before, who introduced MXenes in very detail, but a couple of things I want you to remember about these materials through the talk, because they will be important. So first of all, it's a big family of two-dimensional materials. Second, they offer big variability and precise tunability of properties such as elemental composition. So you can have different M elements listed here. You can have a choice between two different X elements. And they also offer precise tunability of their monolayer thickness. For example, you may have same composition, titanium carbon, and several MXenes of this composition. Titanium 2C will be 3 atomic layers thick, titanium 3C2 will be 5 atomic layers thick, and now we can produce thicker layers, 5 and 9 atomic thick layers of titanium carbide MXene, and same for other materials. And the last important thing about MXenes that you need to keep in mind is that their surfaces are covered by functional groups. Potentially, these functional groups are also tunable, but it turns out to be not an easy problem to solve. So as I said, part of our activity is related to modeling, and this is what I will start with. We used modeling molecular dynamics to measure mechanical properties of MXenes. This is what we start with about 6 years ago. And at that time, there was no parameterized force field for MXenes. Now we can use ReaxFF. But at that time, we started to play with a combination of different potentials. So for example, we used embedded atom potential for titanium-titanium interactions. Titanium-carbon interactions we described by a combination of Lennard-Jones and Axelrod-Teller three-body potential. And for carbon-carbon, we used very simple Lennard-Jones potential. So this was our functional for potential energy in MXenes, and this is our simulation setup. So we used quite large sheets of MXenes, 38 by 33 nanometers. For simulation, it's quite large because the number of atoms is around 50,000 to 90,000 atoms, depending on which MXene we use. Simulations were done in NBT ensemble, and we used our own in-house written C++ code for this simulation. So it's massively parallel code. And mechanical properties we calculated using virial theorem. For example, stresses were calculated using this expression. This is very much known procedure. The advantage of using computational modeling to simulate MXene behavior is that you have full control and full information about what is going on in your material at the atomistic scale. So here I show a movie of stretching of 3 different MXene monolayers. Titanium 2C is on the left, then titanium 3C2 in the middle, and titanium 4C3 on the right-hand side. And you can see, even by looking simply at how they fail, of course, when you stretch them, eventually they fail. The failure mechanisms are very different between these 3 MXenes. Now, they all have same elemental composition. It's titanium carbon MXenes, right? And the only difference between them is the variations in monolayer thickness. As I said, MXenes allow precise tuning of this. And so you not only can use this modeling to get information about failure mechanisms and mechanical properties of these MXenes, but you can also use the MXenes as models of materials with precise control of monolayer thickness. So this is a very interesting aspect, which I will return again and again in the talk, that MXenes we can also use as models, convenient models for fundamental studies of any property which depends on the monolayer thickness, of course, including mechanical properties. Since we can measure stress and strain during this in silicon experiment, we can produce stress-strain curves, and these curves give you information about mechanical properties. For example, the slope of initial part gives you Young's modulus, and you can see the values here for 3 different MXenes. Behavior of these stress-strain curves at different strain rates tells you something about elastic and plastic deformations of the materials. And as you can see from these curves, at lower strain rate, the materials behave more plastically. So this is what we usually observe in metals. And this is consistent with basically metallic nature of MXenes, because they also offer very high conductivity, and electron density at Fermi level is very high. So this is another illustration that they behave basically as metals when you deform them, especially at low strain rates. So you can get information about Young's modulus, about failure mechanisms, and the values of Young's modulus that I showed in previous slide were later on also confirmed by ReaxFF modeling that Yuri presented last time, and also by experiments also done by his group in collaboration with a group at the University of Nebraska-Lincoln. Those were first measurements of Young's modulus on monolayer MXenes, and the values were surprisingly actually close to what we predicted using this simple molecular dynamics modeling. Next thing that we also worked on using modeling was bending rigidity of MXenes. And bending rigidity, the concept is intuitively is very simple. So if you have a very thin material, right, then you expect it to deform very easily when you try to bend it. And when you have a thicker material, then it will take more force or more energy to bend it. So this is bending rigidity in simple words. If you want a way to calculate it, here is the equation which allows you to calculate it. So D is bending rigidity here. And if you know the force F and displacement W, and also the length of your plate, so again, you model your MXene monolayer as a plate, you can calculate D bending rigidity using this equation. And this is how we have done it from molecular dynamics, because again, we can measure force, which is required to deform MXene as shown here to a certain extent. So this is the extent of deformation, 0.3, 0.7, 1, and you see we bend it more and more. And of course, we need more and more force as shown on these graphs. And then from these graphs, you can determine bending rigidity. So we have done it. And it turns out that bending rigidity values are very, very high. This is the range, sorry, I put the same number twice. Of course, it makes no sense. So it's around 49 to 50 something electron volts for different MXenes. And if you look at these numbers, they are much, much higher compared to graphene. Well, that is expected. Graphene is very flimsy, monoatomic layer, thick material. But even compared to moly disulfide, the numbers for MXenes are much higher. So MXenes are predicted to be much more rigid than other 2D materials. And this is important because in certain applications, especially when you want your material to maintain, for example, high frequency of vibrations in sensing, graphene is not a good choice for that, because graphene cannot maintain high frequency of vibrations. It will vibrate at very low frequency because it's very flimsy material. But MXenes may be better materials for that, because they have much higher bending rigidity and therefore are expected to maintain much higher frequency of vibration. So again, important for sensing. So this is the part that I wanted to show you related to modeling. Now we are going to switch to experiments with MXenes. We also do a lot of experimental science with MXenes related to mechanical properties, to tribology. And here's one example where we measured adhesion between MXenes and other materials. So in this experiment that is shown here, we used AFM tip. It's silicon tip with a native layer of silica oxide on it. And we measured force required to detach this tip from MXene monolayer deposited on the substrate. So what happens is this: when your tip approaches your material, of course, there are van der Waals interactions and other interactions which result in adhesion between the tip and your material. And then when you try to retract your tip, as shown here, so this is the state at which your tip is in contact with your material, then you try to retract your tip. But it requires force, okay? It requires force that is larger than 0 because you have to overcome this adhesion. And then eventually, if you keep increasing the force, retracting force, at some point your tip just jumps off your material. So this dip corresponding to jump off phenomenon can be used to measure the adhesion force. So this is basically the magnitude of the adhesion force between your tip and your material. So this is how we have done these experiments using AFM, and here are results for different materials. So we have bare silicon tip here, and then we have 3 different MXenes: titanium 2C, titanium 3C2, and titanium 4C3. And you can see that actually all these graphs demonstrate different magnitude of jump off phenomenon, and therefore you expect different forces. Moreover, for some of these materials, the force depends on the number of monolayers. So we have monolayer or bilayer or 3-layer materials here, and they produce different jump off curves. Now, when we started to look deeper into this, it turns out that for materials like graphene, we observe this dependence of adhesive force on the number of monolayers in the stack. And the dependence in this, when we go from monolayer graphene to bilayer graphene, the adhesion increases dramatically. Then we go to 3-layer or 4-layer or 5-layer graphene, and adhesion force doesn't change much. So for graphene, the behavior is this: initially, the adhesion is very sensitive to the number of layers in the stack, right, going from mono to B. But then this effect disappears. Starting from 3-layer and more layers, the adhesion force is constant. For MXenes, what we found is that no matter how many monolayers you stack, so the data are shown here. So this is titanium 3C2, titanium 2C MXenes here. So no matter how many monolayers you stack, the adhesion force or energy in this graph is essentially constant. Whereas for graphene, so here is monolayer here, and then bilayer, and you see how adhesion energy changes. Okay, so for graphene, the change is very significant, whereas for MXene, it doesn't matter how many monolayers you stack, the adhesion force doesn't change. And then we started to think about why in graphene we don't observe this behavior, and we came up with a hypothesis that this effect of, we call it number of monolayers effect on adhesion force, it depends significantly on the thickness of your monolayer and interlayer distance. So basically, adhesion interactions in case of graphene propagate deeper than the topmost monolayer. Why? Because the monolayer is just atomic layer thick, so it's very thin, and the interlayer distance between graphene monolayers is also very small compared to MXene, where even the thinnest MXene, titanium 2C in our experiment, has already 3 atomic layer thickness, and the interlayer distance between the flakes when you stack them is also much larger than in graphene. And it turns out that if you calculate the lengths over which this additive effect on adhesion force propagates in graphene, which schematically is shown, this length is shown by the length of this arrow, then if you apply that same length for MXene, it turns out that this length is completely covered by just one monolayer of titanium 2C. And then it doesn't matter what you have beneath this monolayer, your tip simply cannot feel the effect of these monolayers beneath because the distance is already too much, even with one monolayer. So that was our explanation for the absence of this number of monolayers effect. And we have also discovered other effects. For example, adhesion increases with the monolayer thickness in case of MXene, but not with the number of monolayers of MXene stacked in van der Waals stack of these materials, okay? And also another interesting observation that we made also in this paper in Nature Communications a couple of years ago, that adhesion force between MXene and silicon, for example, is similar to adhesion force between graphene and silicon, which makes it possible to fabricate heterostructures of these materials. So we can fabricate graphene on silicon and then put MXene on top of graphene and then put graphene again, which is critical if you envision applications of MXenes in electronics, because this is how we fabricate all components of electronics. It's just stacking of different layers, right? And it's very important that the adhesion strength is similar for graphene and MXene, because it tells you that you can seamlessly integrate all these materials, graphene, other MXenes, without developing mechanical strengths between them due to differences in adhesion. We also studied properties of multi-layer MXene films, which we fabricate using interfacial film deposition. And the way we studied mechanical properties of these films was by using a device which is called push-to-pull device in SEM with pica indenter. So here is the pica indenter, which we use as a source of force. It basically pushes with a given force on this part of the push-to-pull device, which is shown here, and its schematic is presented here. And the essence of this device is that when you push on this part, it basically stretches the material which is deposited here. It's just the design of this device is such that by pushing on one side, you stretch the material which is deposited over this gap. And we deposited MXene films over this gap, again, with precisely controlled number of MXene monolayers, as you can see here, 1, 2, 3, 4, 5 layers, right? So we know exactly how many layers we have in this MXene film. And then we start to stretch it with, again, known force, and we observe how it behaves. So eventually, of course, it breaks when we stretch it above certain limit. But then again, we have, before that failure happens, we can record data on force and displacement and produce, again, stress-strain curves. But now these curves are for multi-layer MXene films with precisely controlled number of monolayers. And here I show it for two different MXenes, titanium 2C, titanium 3C2, and different number of layers. So all curves demonstrate similar linear response at the beginning, which we can use again to calculate Young's modulus. But then we observe non-linear stage, and the samples with more layers become softer beyond a certain strain, of course, and that limit after which they become softer depends on the number of monolayers. Okay, so I'm talking about this part of the curves now. When it starts to deviate from linear, so this is softening phenomenon, and you can see that all samples demonstrated, and the extent to which they demonstrated depends on the number of monolayers. So we started to look into how these stacks of monolayers fail and why they demonstrate this behavior. And again, we found out that the failure mechanism is basically a layer by layer failure instead of a concerted failure of all monolayers in the structure at once. And this was a reason why we instead of sharp degradation of sample here, it just becomes softer, but still can maintain mechanical load. Now, this is interesting because it tells us that we can fabricate multi-layer structures based on MXene, and we expect that these structures will demonstrate quite high mechanical properties even when they start to fail, because they don't fail all monolayers at once, they fail in sequence. We can expect that even when they start to fail, they will still maintain quite high mechanical strengths. And when I started to look into this data, plotting them on log-log scale as a function of strength or Young's modulus of these films, depending on the number of monolayers in the films and here, we observed another interesting thing about MXenes, which is very different from other 2D materials. When we increase the number of monolayers in a stack, the properties eventually start to degrade. Well, when I say they start to degrade, what do I mean is they start to degrade compared to the additive values that you would expect for this particular number of monolayers. So you know mechanical properties of one monolayer, then you stack 10 of them, you expect that the property will be 10 times more, right? So this is additivity. But what happens with real materials when you stack them, your resultant property is usually much less than additive property. And this is what was observed for other 2D materials. For example, I show data here for molybdenum disulfide, for graphene. So this blue line or black line, this is how your properties basically scale up for these materials when you start to stack them. Instead of additivity, you observe that they actually start to degrade compared to additive value. It also happens in case of MXene, but at much slower rate. As you see, these curves, which are for titanium 2C and titanium 3C2, are much more horizontal. So that means that strength and Young's modulus in MXene stacks is maintained much better compared to other materials, graphene or molybdenum disulfide in this case, which means that MXenes show better scaling up behavior compared to other materials. And then again, we used modeling to understand the atomistic details of what happens in these stacks. And now we used ReaxFF molecular dynamics, and we modeled the stacks of MXene monolayers with different number of layers, two different MXenes. So this is titanium 2C, this is titanium 3C2, different number of monolayers. And again, we can calculate stress strain curves. And what was interesting is that these curves demonstrated pretty much same shape and same behavior as what we observed in experiment. These are experimental curves. These are our calculated curves. We were very encouraged by this fact, and then we started to look into mechanisms of failure, and indeed we observed that in the stack, say for example, when we have say 10 layers in the stack, the failure starts in one layer first, and then it propagates to the next layer and to the next and to the next. So this is what is responsible for this softening behavior, where your material becomes softer, but it doesn't fail completely. Okay, so it was confirmed with modeling at the atomistic scale. And then finally, when we looked closer at the edges of the forming cracks, we found another interesting effect. And that brings us back to the very first slide about MXenes, when I said it's important to remember that the surface is coated with functional groups. And here we observe this effect of functional groups on mechanical properties. So what happens is this: when you stretch MXene and it starts to break and you form the crack, then oxygen-containing groups, which are attached to titanium atoms, oxygen is two-valent element. It prefers to form two bonds, right? When you start to separate titanium atoms between the edges of the growing crack, then what oxygen does, it basically connects one titanium atom on one side of the crack to another titanium atom on the other side of the crack. And in this way, it also maintains mechanical stability of this material. So this is another reason which may lead to softening behavior, but not abrupt failure as you would expect for graphene, for example, or other 2D materials which do not have these functional groups on the surface. So the presence of functional groups on MXene surface becomes important in mechanisms of failure of these materials. Okay, so this is another insight from modeling. And the last part I'm going to talk today is related to tribology, and this is very recent work which we have done in collaboration with Anirudh Hasuman, who is pictured here measuring from Argonne National Lab. So in this work, what we have done, we measured tribological properties of MXene films deposited by spray coating. So here's the schematic. And we tested them using a ball-on-disc tribometer against DLC-coated steel balls in a controlled environment. Now, these are the data which we observed when we tested these films in dry nitrogen atmosphere. So I have to tell you this first. When we tried to test these films in just ambient air, nothing interesting happened. They degraded fast and the performance was nothing impressive. But then when we switched to dry nitrogen atmosphere, we started to observe very interesting effects. So here is coefficient of friction for bare silicon without MXene. And here is what happens when we deposit a thin layer of titanium 3C2 MXene on that silicon wafer and test it. So you see that when we deposit MXene on silicon, the coefficient of friction after initial run-in drops below 0.01 and stays at that value for the whole duration of testing until the coating eventually fails here at around 3000 seconds in this case. But this value below 0.01 corresponds to superlubricity. So this is coefficient of friction of this MXene film, and this is the coefficient of friction of just bare silicon. And then we also coated MXene film with a film of graphene. And interestingly, we observed same superlubric behavior. So now it's this green curve, but the film maintained its performance for much longer time compared to the original film. So again, this is the coefficient of friction of the MXene graphene coating, still in superlubric region, but now we also have other benefits. For example, addition of graphene also reduces wear of the ball. So this is the wear of the ball with which was rubbed against MXene coating. This is against silicon, of course, very large wear. MXene less, but still quite large. When we add graphene, the wear becomes very small. So the data are also shown here. Ball wear rate. Okay, so MXene itself shows this value, but when we add graphene to it, then the value becomes much less. And importantly, we still maintain superlubric behavior offered by MXene. Graphene itself did not show superlubric behavior in these experiments, but when we coated in graphene on MXene film, then we achieved both superlubric behavior due to MXene and very low wear rate due to graphene. So we observed, again, superlubric properties in the atmosphere devoid of oxygen and humidity. And addition of graphene also protected MXene film and reduced ball wear rate. Now, when I say protected, what do I mean? Well, this brings us back to understanding why MXene did not demonstrate superlubric behavior in just ambient atmosphere, because we hypothesized that MXene may actually react with humidity and air in the environment. And over the past few years, we looked extensively into chemistry of these interactions, and it turns out that yes, MXene does react directly with water, which we call hydrolysis, and it also can be oxidized by air. Well, this is another big part of research activities in my group, which I am not going to cover, but if you are interested, just go in and read these papers. This is just an example of how to suppress hydrolysis. If you simply change water to non-aqueous solvent, then your MXene becomes much more stable, even if you saturate this solvent with pure oxygen, compared to water, Even when you degas water with argon, MXene degrades quite fast in water. So it makes sense to protect MXene with graphene if you want to use it in ambient environment. And actually, when we published this work, it was around the time when Perseverance rover landed on Mars. And I thought that this is a perfect example where you can use these properties of MXene as super lubricant, because when you are in space, you don't have water and you don't have oxygen in that environment. So this is exactly an environment which is good for MXene to demonstrate superlubricity. Even on Mars, you don't have much oxygen and not much water to degrade it. So this may be one of the best materials for lubrication in space, where many other lubricants fail. And this brings me to conclusions of this talk. So first of all, I think I introduced again MXenes as a large family of 2D transition metal carbides and nitrides, which opens up a huge playground in mechanics, tribology, and mechanochemistry of materials. Remember that we can do many fundamental studies, and they will benefit if we use MXenes for them. They will benefit from precise tunability of monolayer thickness, elemental composition, and surface chemistry. And from the standpoint of applications, what we know now about MXenes is this, that they have quite high Young's modulus and fracture toughness, and show better scaling up behavior compared to other 2D materials, which makes them actually interesting candidates for composites, coatings, basically any structural applications. They also have a beneficial and tunable adhesion with other 2D materials and with silicon, which makes them ideal materials for fabrication of heterostructures for optoelectronic applications. Again, no stress due to mismatch in adhesion. And finally, superlubricity of MXenes is very interesting because it's maintained in extreme environments, which makes these materials promising candidates for applications, say, in space exploration. So I'm going to conclude acknowledging help from my collaborators, Professor Qingling Wu from Missouri S&T, Dr. Nirut Hasuman from Argonne National Lab, and Dr. Kalyan Mutiala, also from Argonne National Lab. Students who have contributed to results presented in this work, Shaohan Huang, who is now actually a professor at Donghua University, and Yangxiao Li, who is Professor Wu's student, and also acknowledge support from NSF for studies of mechanical properties of MXenes. And that's all. Thank you all for your attention. If you have any questions, I'll be happy to answer either now or at the end of this webinar.
Yeah, thank you very much, Vadim, for this beautiful talk, unifying numerical and also experimental work. Are there any questions right now, or shall we just move on to the second talk, since Ashlie also already joined the meeting? Maybe we can use this opportunity to move on to the second talk, and then we do the questions at the very end.
All right.
So now I give the word to Philip, who's going to introduce our second speaker, Professor Ashlie Martini.
Yeah, first of all, welcome, Ashlie. Thanks for joining us. And ladies and gentlemen, let me introduce our next speaker now, who is Professor Ashlie Martini. Professor Ashlie Martini is a professor of mechanical engineering at the University of California, Merced. And the research of her group focuses on solid and liquid lubricants, on tribochemistry, as well as nanoscale contact and sliding. To understand fundamental mechanisms of tribological phenomena, they use multi-scale simulations and measurements. For more info, please, for more info on the research of her group, please visit her website, or also the Martini Research Group on LinkedIn. They have some really great, interesting, and also funny material on there. Professor Martini is currently one of the most cited researchers in tribology, and she has also authored more than 200 research papers and is coming close to an age index of 40. Today we will hear her talk about the atomistic mechanisms of friction for MoS2 and beyond. And I guess she has also to say some words about the Mars rover. Yes, please, Ashlie, the stage is yours. We're very much looking forward to your talk.
All right, thank you so much. Thank you so much for the invitation. Let me go ahead and try to share my screen. Oh, host has disabled screen sharing.
You were just
now you can go ahead.
Okay.
So it should work now.
I can feel some resistance to what I have to say already. Okay. Please let me know if you can see it.
Yes. Not yet in full screen though.
How about
yes,
there?
Is
that good?
Yeah. Yeah.
All right.
Perfect.
So thank you everyone for being here. Thanks for listening to what I have to say about atomistic insights into friction on MoS2 and beyond. Everything I'm going to be showing you here today was done by my recently graduated PhD student, Mohammad Vazer-Sereshk, and in collaboration with Rob Karpik and his research group at the University of Pennsylvania. So I'm starting off with molybdenum disulfide, or MoS2, and this is a layered structure comprising sandwiches of molybdenum and sulfur. As shown on the right, there are several different crystallographic phases that can be achieved both naturally as well as synthesized. They proffer various material and electronic properties ranging from metallic to semiconducting. But from a tribological standpoint, which is my main focus, the key feature of MoS2 is the layered structure. Like other two-dimensional materials, MoS2 has strong covalent bonds within the layers between the MO and the S, and relatively weak interactions between the layers. This enables the material to slide to shear relatively easily between those layers at the weak bonds. From an application perspective, MoS2 is used as a lubricant additive. In fact, it was patented for this purpose nearly 100 years ago. Today, it's used as an additive in lubricating oils, greases, as well as top treats, mostly for specialty applications, some of which are shown here. The other application of MoS2 is as a coating or a solid lubricant or a dry film lubricant. The prototypical example here, as mentioned in the previous example, is space, where it's very cold such that one may not be able to use a liquid lubricant. Shown here on the left is an example from the James Webb Space Telescope, and in the middle is a bearing coated with MoS2 to be used without liquid lubricant. On the far right is an SEM close-up view of an MoS2 coating where you can see the lamellar structure evident in the crack that we're illustrating there. So despite the use of MoS2 and the great promise for many different applications, design of MoS2-based systems is difficult because tribological behavior of MoS2 depends on, well, like everything. It depends on temperature, it depends how it's synthesized, the environment. It even depends on how rough the substrate is. Shown here is just one example where you're looking at friction on MoS2 deposited in different ways and in different atmospheric and temperature conditions. And you can see a vast array of frictional behavior. This is a challenge when using or planning to use MoS2 as a lubricant. One approach to capturing these complex interrelationships is empirical modeling. I'm showing you here just one example of shear strength or frictional resistance as a function of temperature, where the experimental data was fit to the equation shown on the right. The fit parameters in this case were informed by atomistic simulations, but nonetheless, this is a good example of taking experimental data and fitting it such that one can use the fit equations to guide design. And this approach is widely used and is very appropriate for one parameter or perhaps even a few. However, I propose that to complement experimental measurements and empirical modeling, another and complementary again approach is to break down this very complex system into sort of a fundamental single unit of tribology. So if we think back to that bearing on the that I showed you a few slides ago, the actual contact is comprised of many different asperities. If we break that down and we focus on just one single asperity, the premise is that if we can understand MoS2 sliding behavior at the single unit of friction, perhaps we can extrapolate that information upward and complement empirical modeling for design purposes. In terms of research, the single asperity studies are realized primarily using two tools. The experimental tool is the atomic force microscope, where we have a nanoscale probe sliding along the surface, where that nanoscale probe is your single asperity. And I will again mention up front that the AFM results I'm going to be showing to you today are from Rob Karpik at UPenn. The AFM experiments are often complemented by molecular dynamic simulations of the apex, or just the bottom of the tip, and the surface on which you're sliding. So together, these two research tools can be used to fundamentally understand friction at the atomic scale. I've given many talks where I discuss or describe how to create these matched models, these matched AFM and molecular dynamics. And here I just want to make one quick point that when we say sliding or friction on or friction of MoS2, for example, really what we mean is friction between two things. So any good model must capture both the material of interest, in this case MoS2, as well as the tip. And shown here are just a couple examples where we've taken transmission electron microscopy, TEM views of the tip to design and model as accurately as possible the apex of the tip in terms of material, crystallographic direction, so on and so forth. And this is incredibly important for using AFM and MD as research tools together. So what's really important about this single asperity approach is illustrated on this slide. So shown on the left is our AFM results, and on the right are complementary molecular dynamics. The top two images are friction maps, and the bottom two are friction traces, meaning a one line across the top one. The key feature in the lower images is the sawtooth pattern, and this corresponds to the tip sticking and slipping across the surface. The key feature here is that the periodicity of the stick-slip patterns corresponds to the underlying atomic lattice. This is a really powerful idea because we're trying to take this very complex frictional behavior and correlate it to a ground truth, to something fundamentally known. And there's nothing more fundamental than atomic lattice. So achieving this so-called atomic stick-slip is very important for using the single asperity approach to understand friction at a fundamental level. Shown here are some representative AFM results, again from Rob Karpik's group. What you're looking at is friction measured at different speeds and different temperatures. And in each case, you see the sawtooth pattern indicating that the friction is correlated to the atomic features of the surface. And we see here that although we were trying to simplify things, in fact, the single asperity friction does reflect some of the behaviors observed on larger scales, namely the temperature and speed dependence. But to get back to something fundamental, again, correlating friction to atomic features, we did a study focused on the direction dependence of sliding. So shown on the left, in the lower left image, is a schematic of the topmost layer of MoS2. And what you can see is that conceptually speaking, there's two directions that you might be able to slide that would conceptually give you very different friction. In one, you have to overcome more, we'll say, atomic obstacles, meaning there should be higher friction. Right? Shown on the right are two representative results from the AFM experiments and the molecular dynamic simulations. And you can see that in one of the scanning directions, we have very high friction, and in the other scanning direction, we have very low friction, reflecting the underlying atomic lattice of the MoS2. We repeated this experiment in all of the different possible sliding directions. And what we were expecting is that we would have 6 low friction directions based on the 6-fold symmetry of the MoS2 crystal structure. But instead, in both experiments and simulations, and on both bulk and monolayer MoS2, we saw only 2 low friction directions. This was quite confusing to us because, again, we're trying to connect friction to atomic structure, and we see some seeming discrepancy here. To understand this, we looked at potential energy surfaces. So these colorful schematics that you're looking at on the left are the potential energy of the MoS2 surface. The one on the left is the ideal structure where the red is high energy corresponding to the positions of the sulfur atoms in the topmost layer. And you can see that there should indeed be 6 ways you can go from the center line and get low friction. However, recall that I told you that friction is not just one material, it's 2 things sliding relative to one another. So we recalculated the potential energy surface using the model tip in the simulation and found a very different story. Specifically, we found that the tip breaks the 6-fold symmetry and that that leads to 2 directions of low energy corresponding to our 2 directions of low friction. So it seems here that surface energy, again, something fundamental about the material, plays a very important role and potentially is a link between friction and atomic nature of the materials. To take this one step further, we did a study comparing MoS2 and graphene, or graphite. So the 2 prototypical 2-dimensional materials are MoS2 and graphite, and these indeed are the ones that are used in practical applications today. What we wanted to do was do a head-to-head comparison such that we could differentiate between their frictional behavior and correlate that to differences in their fundamental structure. This study was made possible by samples that were synthesized at Charlie Johnson's group at the University of Pennsylvania. What you're looking at on the left are optical images of these samples, and what you can see is that they deposited both graphene and MoS2 on a silicone substrate. The reason this is a very powerful and exciting sample for us is that if you look at the image on the right, the close-up view, you can see that along that scan line drawn by the blue line, you can slide with the AFM tip along one direction and cover MoS2 on silicone, MoS2 on graphene, and graphene on silicone. So we can really do a head-to-head comparison between graphene, MoS2, and them together, which I'm calling here a heterostructure. Shown here are the results of one such measurement. On the left are the experiments, and the right are the simulations. And the friction corresponds to the line that you're looking at. And what you can see right away is that both in the simulations and the experiment, there's higher friction on the MoS2 than the graphene. Maybe there's a bit of difference in the heterostructure, but it's not evident in this particular analysis. But right away, we can see that there's some contrast between the MoS2 and the graphene. This was repeated along multiple scan lines in the experiments and at many different loads. So what I'm showing you now here, again, the left is the experiment, the right is the simulation, is the comparison, friction as a function of normal load between the MoS2, the graphene, and the heterostructure. And you can see here across all the loads, the MoS2 has higher friction than the graphene. And in some cases, you can see that within the error of either the experiments or the simulations, the heterostructure has slightly lower friction than the MoS2. To explain this difference, again, we're trying to use energy as the link between friction and atomic features. We looked at our potential energy surfaces. The colorful images are the maps, the energy maps, and the lines below them are a line profile across the high energy barrier. And we can see from our empirical potential in the MD simulations, there's a higher barrier for sliding, a higher energy barrier that has to be overcome to slide on the MoS2 than the graphene. Again, this is an empirical model, so we obtained corroboration from density functional theory calculations performed by Aaron Johnson's group at Dalhousie. Those are shown over here on the right. And you can see, in this case, the DFT approximated the tip as a methane molecule. And you see 2 different orientations. In both cases, the energy barrier for sliding is higher for MoS2 than graphene. So you may be thinking, well, sure. There's lots of differences, though, between MoS2 and graphene, right? Not just their crystallographic structure, and potentially not just their energetics. So we took one step further, and we performed a study comparing transition metal dichalconides. So this is a class of layered materials of which MoS2 is one, all right? Here we compared 3 different TMDs, the sulfur, the selenium, and a tellurium to get MoS2, MoSe2, and MoTe2. You can see here the lattice parameters on the right. They have the same crystallographic structure with slightly different lattice spacing. So now we're kind of removing some of the possible reasons for differences, and we're isolating it to just the lattice parameter. Shown here are the AFM results. On the far left, we see a friction map where we see the atomic stick slip features, indicating indeed our friction can be correlated to atomic properties. In the middle, you're looking at the lateral force as a function of scanning distance, again from AFM, and we see, surprisingly, that MoS2 has the lowest friction and MoTE2, excuse me, has the lowest friction and MoS2 has the highest. This was repeated in the simulations. On the far left is a schematic. In the middle, we see the simulation results. And again, the MoTE2 has the lowest friction of the three and the MoS2 the highest. We repeated the simulations in different scanning directions and found that sliding in any direction except the one low friction direction, we see the same trend of MoS2 being lowest and MoS2 being highest in terms of friction. In the one very low friction direction, the friction was so low that we really couldn't differentiate it. We analyzed all sorts of different possible explanations for this contact size, substrate deformation, force distributions on atoms. None of them really explain this somewhat surprising trend. So we came back to our potential energy surfaces. What I'm showing you here, the colorful pictures are the potential energy surface. That is the convolution of the model tip and the substrate, where red is high energy and blue is low. The black line is the trajectory of the tip as it moves over the surface. And below you can see the corresponding lateral force or friction trace. There's two key points to note here. First, the difference between the maximum and minimum energy, so the energy barrier height on all three of these TMDs is about the same. But secondly, the tip doesn't actually go over the high energy barriers. Rather, it goes around the high energy barriers and crosses at the saddle points. We then compared directly the energy at the saddle points. So on the far left, you're looking again at those potential energy surfaces. The black lines are the tip trajectories, and we analyzed the energy at the position where the tip actually moved. And you can see in the middle figure that even though the height of the barriers was about the same, for the MoTE2, the width of the saddle point was the largest. So this can be directly correlated to the fact that MoTE2 has the largest lattice spacing. So what we're seeing here is that among these three transition metal dichalconides, they have similar structures, similar energy barrier, but because of the width of the saddle caused by the lattice spacing, it's easier to move forward on MoTE2 and we have lower friction. To try to generalize this trend, we turn to the Prandtl-Tomlinson model. For those of you who may not have heard of this, this is an approximation or a simplification of an AFM experiment in terms of a point mass being dragged along a potential energy surface by a harmonic spring. The parameters in the model, there's very few. There's the speed, the spring constant, and then the two that are most relevant to our study, which are the height of the energy barrier U and the lattice spacing A. Recall that our tip didn't move along a straight line, so we extended this to a two-dimensional Prandtl-Tomlinson model. It's basically the same as the one-dimensional, except the sinusoidal profile goes in both directions. And again, we're capturing the height of the barrier with U and the lattice spacing with A. And just a quick note that these were done using MATLAB codes that are available as in the supplemental material of the reference shown on this slide in case you want to repeat the experiment. So let's look at the Prandtl-Tomlinson results. On the far left, you're looking at a friction map where we have energy and a lattice constant, and the friction magnitude is reflected by the color. On the far right, we see friction as a function of energy barrier. So as one might expect, the higher the barriers, the higher the friction. But the more interesting plot perhaps is the one in the middle, where we see friction as a function of lattice spacing. What this tells us is for materials that have similar energetics as for our three TMDs, friction will go down with lattice constant. And now we know this is because it allows the tip to more easily move through these wider saddle points. All right, so I titled this presentation MoS2 and Beyond. So let me quickly do the beyond part. The study I just showed you already probably has your mind turning about the possibilities for transition metal dichalconides. This TMD family, we only looked at 3 of them. However, there's sort of not an infinite, but there are many possible combinations of metals and chalcogens that you can put together in this similar structure, getting layered materials that gives us sort of a dial that one might be able to turn to achieve designer transition metal dichalconides. And if we can understand how the energetics and the lattice spacing affects friction at the fundamental scale, we can, again, kind of slowly turn this knob to achieve the friction behavior that we wish to have. Another knob dial that one might turn is the use of dopants. And the term here, dopants, refers to the addition of relatively low concentrations of other elements. These other elements may appear within the MoS2 crystallographic lattice. Shown here is a schematic where we see 4 different possible locations for a dopant, and or they can appear as different phases. Regardless, the use of dopants has been found to dramatically affect tribological behavior. On the left image, you're looking at friction as a function of temperature, with MoS2 having various dopants. And quite interestingly, this shows that if you're looking for high temperature behavior, perhaps you're looking at a gold dopant, or the green line here perhaps. But if you're looking at cold temperature behavior, again, back to the example for space applications, then you might be looking for a nickel dopant. So we're very small concentrations of elements, we're completely changing the profile. In the middle figure, you're looking at wear life, so how long it took for coatings to fail. And in this study, we found that particularly for low contact pressures, the addition of a nickel dopant in very low concentrations dramatically increases the life. So this gives us, again, another dial to turn to change or tune tribological performance. Lastly, now that there's all these 2D materials, right, there are graphenes and graphites, we have the transition metal dichalconides, we have our doped materials, we have the MXenes as presented in the previous discussion. These things can be combined into heterostructures. So the example I showed you was just the graphene and the MoS2, but you can take all of these ideas that I've presented and potentially, build them up as shown in the schematic here with the Legos to create and achieve the tribological performance that you wish. So to wrap everything up, MoS2 is already being used as a lubricant additive as well as a coating. It already lowers friction and wear for tribological applications. One of the challenges for using MoS2 and similar materials is that their performance really is highly dependent on almost everything. And it's a huge challenge in terms of, as from an engineering design perspective, to design with all these kind of unknowns. So the approach that I've presented here, and I hope I've convinced you of, is that you can break these very complex things down into the single unit of friction, the single asperity, which is realized using the AFM and complemented by molecular dynamics. If you can understand the relationships between friction or wear or whatever tribological property and ground truth fundamental properties of the materials, for example, the lattice spacing, then we can maybe take one step further in terms of designer materials and rational design using 2-dimensional materials with very tunable tribological properties. So lastly, thank you so much for your time here today. Those of you watching live are welcome to ask questions, but you can also just send me a quick note at my email. Thank you.
Thank you very much for a very interesting talk, Ashlie. And also, of course, thank you, Vadim, for the nice talk. If you have any questions now, addressed to the audience, you can either ask them live or you write it in the chat and we'll pass it along. And be sure to also indicate to which speaker your question is addressed. That would make our life a lot easier.
We have already the first question in the chat, and I think this can go to both of them. So what is the fundamental difference between 2D TMDs and MXene? Can we create hierarchical composites with TMDs as can be done by inserting other material in MXenes?
Go ahead, Vadim. This seems more in your area of expertise.
Okay, I'm not sure. But anyway, if I would go first, I would say this. Well, fundamental difference you know, besides both being 2D families of materials, everything else is different. So what do you mean by fundamental difference? Elemental composition is different, type of bonding is different. Functional groups, MXenes usually always have functional groups, TMDs usually don't, right? Other things probably are also different electronic structure and so on. But so there is a lot of fundamental differences. But can we create hierarchical composite with TMDs? This can be done by inserting other materials in MXene. Well, MXenes can be intercalated first with other molecules, if this is what you mean. And they also can be assembled in heterostructures with other materials. Okay, you cannot intercalate materials in MXenes, but you can assemble structures of MXene and say TMDs or graphene heterostructures. So that can be done, of course, with MXenes and TMDs, or with TMDs with some other materials, I guess, right? So that would be my answer. And Ashlie, if you have anything to add.
I don't make anything. So I really am not quite at all qualified, but I certainly agree that it's an exciting prospect. And this mixing and matching of materials is going to be an exciting frontier for the field.
Yep.
Thank you. Yeah, there's the next question coming in to Professor Martini. You mentioned that the AFM tip breaks the 6-fold symmetry to a 2-fold symmetry. Does this happen due to the size and shape of the tip, or are there any other reasons?
So it's a good question. It's not a matter of degrees. So anytime there's a finite tip, the energy changes. So unless it's a single atom, in which case you would get the ideal potential energy surface, you're going to break the symmetry. And although I didn't show this, we did observe on the experimental side, as well as in simulations, the same result with different size tips. So on the simulation side, we explicitly modeled a couple different tips. And on the experimental side, you just get a few different tips that were characterized using blind tip reconstruction. So we believe that any finite size tip will cause this effect.
Thanks. There's another question coming in. Do you want to?
Oh,
yeah, I will
I
just.
I can read it.
I will
It's
just
okay.
read it. Okay.
All right. So has macro scale superlubricity been achieved yet? If yes, is this attributed to structural mismatch or some other mechanism? That's a great question. Again, probably not for me. I bet if we did a Google search right now for macro scale superlubricity, we would get quite a few papers. I would say the origins of what's observed as macro scale superlubricity are still being explored. How's that for a politically correct answer?
Yeah, sounds good.
Exciting, but nonetheless, it's a great question and it's an exciting one. Okay. If we stack different 2D materials to create new surfaces, do we expect to actually see the effects of MoS2 that is a few layers below the surface? That's another great question. In the study that we did with the heterostructure, we had the MoS2 and the graphene on the silicon surface. We did see subtle differences between the MoS2 that was right on the substrate versus the MoS2 that was on the graphene. But here we come to kind of a key point that I didn't really touch on too much. When I introduced MoS2, I said, oh, it's great because it slides between the layers, right? And then I kind of did some hand waving and I said, oh, look, the AFM is sliding on the top of the surface. So there's a little bit of a disconnect between probing the surface with an AFM tip and perhaps some of the more practical applications getting to the macro scale superlubricity. For the larger scale applications, what we expect is that the material is transferred. There's a transfer film to the other side such that sliding occurs between the 2D material layers. So in terms of the AFM, I expect it will be a somewhat small effect, but for larger scale systems, more practical applications, I think you can get sliding between layers and have a bigger effect.
Thank you. So maybe one question to Vadim from my side. You showed quite extensive calculations and also measurements for the mechanical properties of MXenes, and then you showed some for the tribological properties. Can you correlate the results you got for the mechanical properties also with the tribological properties?
Yeah, it's a good question again, and we actually did try to correlate, say, Young's modulus and bending rigidity of MXenes to tribological properties. But I think, well, our correlations are very limited at this point because we only measure it in experiment when we measure tribological properties. We only measured like one MXene. And other people also didn't measure many MXenes so far. I know that Andreas, for example, is very active in that. And I think it's coming. We just need more experimental data to make those correlations. Okay. At this point, it's just correlation for one material. It doesn't say much.
Yeah, that's true, of course. Yeah.
I have another question for Vadim, because on one slide you showed the comparison of MoS2, graphene, and two different MXenes for the yield strength and also for the Young's modulus. And you showed this decreasing tendency for MoS2 and for graphene, and for the titanium, or for the MXenes, it was at least to a lesser extent. And then there was another diagram that you didn't talk much about, which was about the Young's modulus, which showed a completely different trend. Because as far as I remember, for the graphene, it also didn't show, and for the MoS2, it decreased. Maybe you can show the slide, and maybe you could comment a little bit on that, because I found quite interesting, because it was quite different from the explanation that you gave.
Let me share. So I think this is what you're talking about, right?
So far,
I'm not seeing your screen yet.
No, so far not.
Didn't share it?
No.
Try again. So zoom and show.
I think now we can see the background of your desktop.
You see it now, right?
Yes, there it is. Yeah.
And I think it's this slide you're talking about, right?
No, there was this trend where you showed the number of layers versus the Young modulus on the right side and the yield strength on the left side. Comparing numerical data, exactly this one. Yeah.
This one, right?
And the diagram on the right-hand side, which shows a different tendency, because the black diamonds, the graphene, is completely different than the blue ones. What is the difference between left and right? Because on the left, graphene and MoS2 show pretty much the same tendency, and on the right-hand side, they don't show the same tendency.
Yeah, well, the difference is we plot different properties. So on the right-hand side, Young's modulus, here it's strength, right? On the left-hand side. And actually these data which are plotted for graphene and for MoS2 are combinations of experimental and modeling results for both materials. We have modeling is open symbols, and experiment is these blue or black ones, right? Now, as you see here for graphene, modeling shows that basically the scaling is similar to graphene, but this is modeling. Real experiments are these black diamonds, and they show that it goes down, right? This is in terms of the strengths. Now, in terms of the Young's modulus, we don't have so many experimental data here, so we don't know how it actually goes, but modeling predicts that it should not degrade much, right? This is why we have this line here. For MoS2, we have experimental data which actually show that Young's modulus also degrades when we increase the number of layers, okay? So again, I think why they look different is because here we basically mainly plot modeling data. We don't have experimental information. And here we plot modeling, which shows, again, horizontal trend, and experimental data, which show decreasing trend. So I think the real effect, if you would have this data for the right-hand side, experimental data, would also show decreasing trend, but we don't have the data at the moment.
Yeah, thank you very much.
Yes, thank you. There's another question for Ashlie.
Okay, so
the energy.
I got it, Philip. Thank you.
Okay.
It's about the energy landscape images. It says, regarding the calculation of the tip sample energy, is it the total potential energy when the tip is sitting on the sample at each location? This is a good question. I didn't clarify this point. It's the minimum potential energy at each lateral position. So if the tip is at one lateral position, it can be moved up and down, and there's a minimum energy at a certain vertical position, and that's the energy reported at each lateral position. So the color maps were achieved through a sort of three-dimensional energetic landscape. We just showed the minimums. Thank you.
Okay, thank you. And also, Ashlie, one question from me to you. So you were also saying that the molybdenum disulfide is basically one of the only layered materials which is used now for tribological applications. And your results showed quite promising friction, especially for the tellurides in comparison with the sulfides also. Do you know how this also is? Is there similar trends also seen on a macro scale? And if so, why are not more tellurides used rather than the sulfides?
That's a great question. I don't know about macro scale experiments on the MOTE2, but it's a good question. And the unfortunately answer might be cost and historical perspectives. Just that, the MoS2 has been around for a long, long time. As I mentioned, it was patented almost 100 years ago. So that might be in part the reason. Even the MoS2 isn't in, you don't just get your oil changed and have MoS2 in the engine oil. It's mostly for specialty applications where people are willing to pay a little bit more. Yeah. But it's a good point, and we consistently saw the MOTE2 being lower friction. So perhaps there are opportunities for folks doing macro scale studies to explore further.
Okay, thank you very much. Yeah, I guess if there's just another question coming in. Let's have this one before wrapping it up.
Which potential was used for the simulations of MoS2 and the SI tip? I think I'm going to defer this one because I showed you, I think, 4 different studies, and we mixed and matched it a little bit there. So I'm going to ask that you check out the references that I mentioned on the papers, on the slides, and check it out directly, or send me an email and I'll give you a thorough response.
Okay, then, yeah, if now there are not any more questions, thanks again very much our speakers, Vadim and Ashlie, for 2 very inspiring and great talks. And yeah, everybody have a great day or a good night, and we'll see and hear you soon.
Thank you.
Yeah, thank you very much also from my side. We also say thank you to our sponsors, Artec from the industrial side, from MDPI lubricants and coatings, and also Frontiers of Mechanical Engineering that help that this webinar is going to happen for the next 10 months more. Thank you very much, Vadim. Thank you very much, Ashlie. It was very nice to see you, very inspiring. As Philip already said, it was a pleasure to have you today. Thank you very much.
Yes, thank you very much.
Thank you.
Take care.
Take care. Stay safe. Bye-bye.
We also invite you to submit your research to 3 current special issues in coatings, lubricants, or frontiers in mechanical engineering. You can find the links to the special issues in the comment section below the video.
Introducing the most advanced universal tribometer, the MFT 5000. With a modular architecture platform design, it is a robust surface testing instrument engineered to evaluate friction, wear, mechanical properties of materials, as well as lubricants over time. The MFT 5000's open XYZ stages and wide range of interchangeable modules and sensors allows users to self-implement and add-on customization, and combines several tribology tools all on one device. These diverse modules accomplish various motions for any application and are capable of speeds from 10,000 RPM to 500 Hz oscillation. The complement sensors achieve millinewton to 12,000 Newton wide force range, with options of strain gauge, piezo, and capacitive multi-dimension force sensors. The lambda profilometer, combined with the patented inline design, coincide to analyze any surface, including glass, with ease. Because of its unique four-imaging modes, the profilometer produces 3D information by creating sub-nanometer surface images automatically. A fully automated and simple software interface integrates the data, enabling researchers to design and conduct tests at nano, micro, and macro levels. To simulate real-life scenarios, the tribometer comes with several environmental control options that allows testing -120 to 1200 degrees Celsius temperatures. These interchangeable chambers are skilled in evaluating high pressure, vacuum, humidity, salt spray, and tribocorrosion conditions. Due to its multiple possible configurations, the MFT 5000 is used extensively across a wide range of industries, including oil, biomedical, semiconductor, coatings, automotive, electronics, materials, aerospace, and many more. On this platform, all types of tribology tests are possible. Our tech instruments, leading innovation in tribology and surface test instrumentation.